Hi everybody. So this next section is on determinants, and so you might wonder, well, what is a determinant? Well, a determinant is a number that can be assigned to a matrix according to the rule given below, and the determinant will tell us some things about the matrix. And you can also, in some cases, think of the determinant as an area or a volume, but I don't think your book gets into that, so we won't really worry about that. But basically, to give you some terminology here, and I don't know if you really have to know this terminology all that well. I'll show you with an example here in just a minute. But if you have the elements of a matrix are Aij, the minor I of Ij is the determinant of the matrix obtained by deleting the ith row and the jth column of A. So if you have some matrix and you delete the ith row and jth column, that will be the minor. And then the cofactor is basically what you multiply the minor by, and that's essentially -1 to the ij. So you'll see that you might get some alternation in the sign here. So, like I said, when you're calculating determinants, basically you're raising I -1 to the I plus j, where you've got a particular row and column, so you're multiplying the particular minor by either a positive or negative, depending on what row and column it's in. So here's a more clear definition of a determinant, right? So if A is an n by n matrix, the determinant of A is obtained by multiplying each element of the first row by its cofactor and then adding the result. So basically, you get what you take when you cross out the row and the column. That will be your cofactor, and you multiply the ij element by the ij cofactor. Again, that might not mean a whole lot. So let's start with something simple. And again, you can really only calculate determinants for square matrices. There may be a way to do it for non-square matrices, but we won't get into that. If A, B, and C, and D are 4 real numbers, right, then this is what's known as the determinant. And this vertical bar symbol here looks kind of like an absolute value. But essentially the way that you calculate the determinant for a 2 by 2 matrix is, again, you basically cross out the row and column that the A is in and then multiply it by the matrix you have left over. Well, again, there's really not a whole lot left over when you do that. So you basically take A times D, and then you would multiply that by +1. And then when you're doing it this way, if you cross out the row and column that the C is in, you'd multiply by B, but because of the cofactor, you have to multiply by negative because this is in the first row and second column, so you're raising -1 to the 1 plus 2 or third power. So essentially for 2 by 2 determinants, what you basically have to do is just take that times that minus that times that. And just be careful how you do this, right? If you do it in reverse order, if you take that times that minus that times that, you'll get the wrong answer. So it's start in the upper left-hand corner, go down like this, and then subtract what you get when you take that times that. So for example, let's say you wanted to evaluate this determinant. You would just take -2 times -1, and then subtract what you get when you take 4 times 3. That'll give you -10. And there is some meaning to this number, some geometric meaning, but we aren't going to get into that for right now. But that's essentially what you do, right? So for example, let's say you wanted to calculate these 2 by 2 determinants, right? For this one, you would just take 1 times 0, which is going to be 0, minus 4 times 2. So that would give you 0 minus 8, which would give you -8. For this one, you would take 1 times -3, and then subtract 2 times 4. So you get -3 minus 8. That would give you minus 11. Here's another example. For this one, you would just take 7 times 5 minus a -3. So watch your plus or minus signs here. And then you'll get 5 minus -21. So that would be 5 plus 21, or 26. And again, like I said, there is some geometric significance to this number, but we're not going to get into that right now. But one thing I wanted to talk about, at least when we're talking about 3 by 3 determinants, we'll get into this in just a minute. But if you have a determinant like this, you can calculate a 3 by 3 determinant by, again, basically taking this element and crossing it out and multiplying it by the subdeterminant or the minor determinant, and then doing the same thing for each column here, right? So you'd cross out the row and column that this entry is in and multiply that by that subdeterminant, cross out the row and column that the A13 is in, and then multiply by that subdeterminant. And again, we know how to calculate 2 by 2 determinants. And I should mention that you can actually do this along any row or column, so you don't have to do it along this first row. You could do it along the first column here, so you could cross out those two values and then cross out those two values and cross out those two values, and you would get the same value there. In this case, you can actually expand along any row or column. In this case, the advantage of this is that if you have a row or column with lots of zeros in it, it's easier to compute that way. But let's look at a particular example here. And again, here's the technical definition. It's basically what I was just saying here, right? So you might have to multiply by a plus or minus depending on what row or column your element is in. So for example, let's say we wanted to, here in this case, we're not necessarily going to calculate the entire determinant, we're just going to calculate the minors. So for example, let's say you wanted to find M12, that would be what you would get if you crossed out the thing in the first row and second column. So the minor in that case would be given by 3, -2, 1, -1, and you can calculate that, again, just like we did for a 2 by 2 determinant. Take that times that, minus that times that. If I wanted to calculate M23, that would be what I get if I cross out the thing in the second row and third columns. Remember, this designates the row and that designates the column. So in this case, you'd get -1 times 1 minus -2 times 2, which would give you 3. So to find the value of a 3 by 3 determinant, again, you can expand along any row or column. In this case, we're just going to go along the first row. And again, basically you just alternate by multiplying by plus minus plus minus. If you really want to calculate this out, you can. But so you take the thing in the first row and first column, cross that out, multiply by the subdeterminant, or the minor 5, 6, 1, 7, and then that would be multiplied by a -1 to the 1 plus 1, because this thing is in the first row and first column. Then what you would do is cross out the thing in the second row and or the first row and second column. That would give you 3, 2, 1, 7. That would be your minor. Again, in this case, you want to multiply by -1 to the 1 plus 2, because the 2 is in the first row and second column. And then in this case, you would again go over to the 1 and then calculate that minor, right, which is 3, 6, 2, 5, and multiply that by -1 to the 1 plus 3, because the 1 is in the first row and third column. So essentially all you really have to do is just alternate, multiply by a positive, -1, positive 1. And if you calculate this out, right, you'll get 5 times 7, which is 35, minus 6, that's where the 29 comes from. You're multiplying that by the 1, and then -1 to the second power is just a positive 1, so you'll get a positive 29 there. For this, you take 3 times 7, which is 21, minus 2, so that will give you 19, but then you have to multiply that 19 times a positive 2, which will give you a 38, and then this -1 to the third power will be negative, so you get a -38 for that. And then here you take 3 times 6, which is 18, minus 2 times 5, which is 10, that gives you 8. Multiply that by 1, and then multiply that by -1 to the 1 plus 4 power. So if you add those together, and so again in this case the -1 to the 4th power would just be a positive 8, and then add those numbers together, and then that gives you the value of the determinant there. And again, you can expand this along any row or column. Again, you could you could do this along another row or column. Like for example, you could do it along the first row or the second column here. So just to show you what would happen if you did this along the second column, right? So you want to again multiply by plus minus plus minus plus minus, right? That's kind of what I meant by this slide back here with the plus minus signs, right? Because you're just raising -1 to sort of the alternative positive and negative values here, right? So that's what I meant by the slide. So so basically what you want to do is you take the -2, so take the 2 multiplied by -1, and then multiply by the row and column you get when you cross out the 2. So you'll get, multiply that by 3, 1, 2, 7, right? Because if I cross out 2, I'll get 3, 2, 1, 7, and then take, so I've got a positive, negative, positive, negative, positive. I've got a positive 5. Multiply that by, if I cross out the row and column that the 5 is in, I'll get 1, 1, 2, 7. So multiply that by the 2 by 2 determinant 1, 2, 7. And then finally move over to the bottom row and cross out the row and column that that's in, and you'll get 1, 1, 3, 1. So I'll get a 6, and then 1, 1, 3, 1. And then again, is this a positive 6 or minus 6? Well, it's plus, minus, plus, minus, plus, minus, plus, minus. So that would be a -6, right? Alternatively, you could figure out, well, what row and column is 6 in, right? It's in the second row and third column. So that would be -1 to the 2 plus 3, which would be -1 to the 5th, which would be a -1, right? But again, it should just alternate plus, minus, because every time you move over a row or down, over a column or down a row, it should just add 1 to the power. So again, you can just alternate signs like that. And the idea, again, like I said, is it shouldn't matter, like I said, which row or column you expand along. So in this case, like I said, if you have a row or column that has all zeros, or a lot of zeros in it, expand along that. Now in this particular case, there isn't any, but we should get the same answer no matter what row or column we expand along. So let's work this out and see if we get the same determinant. So in this case, I'll get -2. If I multiply this out, right, I'll get 21 minus 2. So I'll get 19 for that. And then I'll get plus 5. I'll get 7 minus 2, which is 5. And then here I'll get -6. And I'll get 1 times 1 minus 3, which will be 1 minus 3. So I'll get -38 plus 25 minus 6 times -2. So you get -38 plus 25 plus 12. Right? So if you add those all together, you'll get -38 plus 37, right, which gives you -1, the same thing that we got before, right? So again, it technically doesn't matter what row or column you expand along, so you could just randomly pick. But again, if you do have a row or column of all zeros, it's easier to compute the determinants that way. So let's say, for example, we wanted to calculate the determinant of this matrix. Again, you could do this by expanding along any row or column, but in this case, I just want to expand along the third row. Now, that might not be the best way to do it, right? It might be better to do it this way or that way, because that column contains a 0 and that column contains a 0. But it shouldn't matter. You should get the same answer either way. So if I expand along the third row here, and I guess technically I should add absolute value symbols around this because I'm calculating the determinant, right? The square brackets indicates that it's just the matrix here. But so again, if I expand along this, right, I'd multiply by positive, negative, positive, negative, positive, negative, positive. So I'd take the -2 and multiply that by a positive 1, which would still leave it as a -2, and then cross out the row and column that the 2 is in. That'll give me 0, 2, 5, -1. So calculate that subdeterminant, right, or the minor. You'll get 0 times -1 is 0. 5 times -5 times 2 will give you -10. Then do the same thing with this one, right? I'll multiply by positive, negative, positive, negative, positive, negative, positive, negative. So I'll multiply this by the 1 by a negative here, and then I'll look at that subdeterminant. So cross out the row and column that the 1 is in. You'll get 1, 2, 0, -1. Calculate that. Take that times that minus that times that. And then lastly, multiply the 3 here, right? So if that's positive, negative, that should be a positive. Positive 3 times what I get when I cross out the row and column that the 3 is in, which is 1005. And there are shortcuts for calculating determinants. Especially in the 3 by 3 case, there's a diagonalization method that you can use. But unfortunately, that does not extend to determinants of higher order. So if you have like a 4 by 4 determinant, you can't calculate it that way. So just something to be aware of. So if you work this out, right, you'll get you'll get basically -2 times -10, -1 times -1, and 3 times 5, which will give you that. And again, you could expand along another row or column also if you wanted to. You should get the same answer. And again, you might wonder, well, what does that number mean? Well, like I said, we're not really going to get into that, but we will see how we can use determinants to calculate some things here in just a minute. So let's look at an example of the same determinant here, but let's expand along the first row. So this is the same one we just did, right? So just to show you that it doesn't matter what row or column we expand along, right? If I do the same calculation, expand along the first row, right, I'll get basically 1 times that. I'll get 0 times that times that. Technically, it should be -0, but negative or positive 0 doesn't matter. So it should be positive, negative, positive. So we'll take a +2 times that minus that times that. If you work it out, you still do get the same answer that we got before. So again, just showing you it doesn't matter what row or column you expand along. That should give you the same answer. Let's maybe just do another example here just to clarify this. So again, there isn't any particular row or column that you need to expand along here, or that might be more advantageous because there isn't really a row or column of all zeros or with lots of zeros. So let's maybe just expand along the first row. So again, I basically just take 1 times 2 times -4, just to speed this up. I won't write out the whole thing here, right? So, which will basically take 1 times this, so you'll get -8 minus 30, then multiply by -4, and then multiply that by -2 times -4, which will give you a +8, and then take 3 times 5, which will give you -15, and then take 8 and multiply that by -12, minus 6, right? So you can kind of speed this up. You don't have to write out every step like we did in the last example. So this will basically be just 1 times -38 minus 4 times -7 plus 8 times -18, and then just work that out, right? So you'll get -38 plus 28. Let's see, 8 times 30, 8 times 18, so it'd be 4, 1, oh yeah, I guess 144, I guess, right? So that'll give you -144 if I did that right. So then you'd basically just get -10 minus 144, which would give you -154 for the determinant there. And again, you could expand along any other row or column. Like I said, there is a shortcut that you can use to calculate the determinant. I mean, there's lots of different ways you can calculate determinants. In fact, Lewis Carroll, the guy who wrote Alice in Wonderland, wrote a whole book on different methods for calculating determinants. But the thing about the 3×3 determinant, if that diagonal method only works for the 3×3 case, so it doesn't extend to higher dimensional determinants. So maybe just to do one more here, again, just to kind of show you how this works, and then you can extend this to any size determinant that you want here. I don't know if I'll have you do this on the exam or anything, but there might be a couple problems like this in the book where you have to calculate a 4×4 determinant. Let me maybe just show you how this works. So, you basically just do what you did before. You expand along any row or any column. So in this case, I think I will just expand along the. This column here, just because it has a 0 in it and the numbers are relatively small. So again, I want to multiply by a plus minus plus, so I'd take -1 and then multiply that by the subdeterminant I get when I cross out the row and column that's in. Right? So if I cross out the row and column that the -1 is in, I'll get 4, 6, 3, 7, 7, 5, 3, -12, 0. Hopefully I won't make any mistakes here. And then you can expand along and then just go down 1, right? So you multiply by a positive, negative, positive, negative, positive, negative, positive. So I'll multiply by a -2, right? Because I'm taking +1 times a -2. So it's a positive, negative, positive, negative, positive, negative. Yeah, so that should be right. And then cross out the row and column that the 2 is in, right? Let's cross out that row and column. That'll give you -2, 3, 7, 7, 7, 5, 3, negative 12, oh, yeah, sorry, 3, negative 12, 0, right? And then just go down one more, go down to here, so you'll get plus or minus 0, it doesn't really matter, times whatever that determinant would be, but we don't have to work it out because we're going to multiply by 0 anyway. So that's what I mean by it's advantageous to expand along a row or column that has a lot of zeros there. And then multiply by 4 here, right? And it should be positive, negative, 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 positive 4, right? And then expand, and then just multiply that by the determinant you get when you cross out the row and column that the 4 is in, right? So you'll get negative 2, 3, 7, 4, 6, 3, and then 7, 7, 5. And then calculate these 3 by 3 determinants, and that will tell you what the determinant is. So let's go ahead and calculate those. So again, you might want to expand along a row or column for these where you have zeros. So let's just expand along this column here. So for this determinant here, I will get, so positive, negative, positive, I'll get a positive 3 times what I get when I take 7 times negative 12 minus what I get when I take 3 times 7, which is minus 21. Right? Then I will multiply by the 5, so again it should be plus, minus, plus, minus, plus, minus. It'll be minus 5 times 4 times negative 12, which would be negative 48. So remember, I got to cross out the row and column that the 5 is in. So I'll get 4 times negative 12 minus 3 times 6, which is minus 18. And then I will just multiply by 0 times whatever this determinant is. But again, I don't need to calculate that because that's just going to be 0 anyway. Then we'll do the negative 2. So I've calculated this determinant. So then we'll do this one again. Let's expand along this column. So it should be plus, minus, plus 7. Times 7 times negative 12 again, and you'll get negative 21 there, and then multiply by 5, so it's plus, minus, plus, minus, plus, minus, it'll be minus 5, right, so it'll be minus 5, sorry, just checking something there, so it'll be a minus 5 times that, so it'll give you a positive 24 minus 9. And then I'll have 0 times whatever, that's still just going to be 0. Then for this determinant I get 0, so I really only need to calculate this one. So it'll be 4 times, again let's just expand along the first row, it'll be negative 2 times 30, right, because there isn't anything with zeros in there, so let's just do it that way. And then it'll be minus 3 times 20, right, 4 times 5 minus 7 times 3, which would be 21. And then finally I'll take a positive 7 and multiply that. 4 times 7 is 28, minus 42. And then just work that out and see what you get, right? So if you work this out, you'll get negative 1, and then you'll get 3. Let's see, 7 times 12, that's going to be what, negative 84? So I'll multiply negative 84 minus 21, which gives me, what, a minus 105? And then I'll get minus 5 times, what's that going to be, minus 66? Hopefully that's right. Sorry, I guess I should have worked this out beforehand. And then in this case, right, you'll get negative 2 times, you'll get 7 times, again, negative 105 again, I think, right? And then you'll get minus 5 times 15. And so you can see it's not that hard. It's just kind of long and tedious to do this. And again, I'm not going to have you do this on the exam. Again, there might be 1 or 2 in the homework where you have to calculate this. And then you'll take 4 times, let's see, what's this going to be? Negative 2 times 9 minus 3 times negative 1 plus 7 times negative see, yeah, it should be. Is it 14? I think, right? Yeah. Okay. So so then just go ahead and work that out further, right? So if you look at this first one here, right, that's going to be -1 times -315 minus 5 times 66. Let me just break out my calculator here. Just to speed things up a little bit here. So if I take 5 times 66, right, I'll get what, 330 for that. And that should be a plus 330. And just be careful when you're doing this, right? Because again, there's lots of plus or minus signs floating around here. It's easy to make a mistake. And then I'll get, so I'm taking, this plus that, so I'll have to add this. So I'll get -2 times 7 times 105. Right, that should be 7 minus 735. And then you get 5 times 15. Right, that's going to be -75. And then you'll have plus 4 times -18 plus 3, and 7 times 14, that should be, what, 98, I think? Yeah, so that'll be a minus 98. And then just simplify that and add all those together and see what you get, right? So this will be -1 times positive 15 minus 2 times, let's see, so -735 minus 75. Combining those two together should give you minus 210. And then you'll get 4. Let's see, if I add those together, I'll get -18 plus 3 minus 98. That will give you -113. So finally working this all out, right, you'll get -15. Let's see, so 2 times 810 will give you plus 1620. And then 4 times 113 will give you a minus 452. Right, so then add all those numbers together, right, and you'll get minus 15 plus 1620 minus 452, and that should give you a value, hopefully, of this determinant of 1153, provided that I haven't made a mistake there. So again, calculating this is very similar to what you would do for a 3 by 3 determinant, and then you can extend this to a 5 by 5 determinant if you want to. So just to show you how how that would work for a 4 by 4 determinant, I think the largest I would have you calculate at something on the exam would be a 3 by 3 determinant. Maybe I would give you a 4 by 4 determinant if there's a lot of zeros, but there might be a couple like that in the homework. So try them and see what you get. If you get stuck, ask me about that. Okay, so another thing I want to look at here is we'll look at this later in one of the later sections. But one thing I want to mention is that if a square matrix has a determinant of 0, that means you can't find the inverse of the matrix. And you might wonder, well, what is the inverse of a matrix? Well, we'll talk about that later. But essentially, if you're given a matrix here and you want to be able to find its opposite matrix, kind of like you did for inverse functions, the determinant has to be non-zero. So if you take 3 times -1, that'll give you -3 minus 2, that would give you -5. So because this determinant in this case is non-zero, this will have an inverse. And again, you might wonder what I mean by inverse. Well, we'll get to that later. So another thing I wanted to talk about here too is that you can do certain row and column transformations and it will leave the determinant unchanged. And so if A is a square matrix and if matrix B, sorry, this should be a capital B here, is obtained from A by adding the multiple of one row to another or the multiple of one column to another, then the determinant of those two things will be the same. So if you multiply a row by something and add it to another row, it shouldn't change the value of the determinant. So not anything that important, but So the main thing that we're going to look at in this section is, so we've looked at how to calculate determinants, and that's all well and good, but the question is, what can you do with them now that we can calculate them? And like I said, there is some geometric significance to determinants, but your book doesn't really get into that. But one thing you can use determinants for is yet another method for solving systems of equations. And again, you might wonder, well, why why again would we want yet another method, right? Because we have, regular elimination, substitution, the geometric method in some cases by graphing. We have Gaussian elimination, Gauss-Jordan elimination. Why do we want to figure out another way to do this? Well, one reason is just to give you an application of determinants. Now, it turns out that determinants can be used for lots and lots of other things, but this is just one application. So basically, what Cramers rule says that if you want to solve a system of equations that has n variables, what you can do is calculate the determinant by taking the matrix that you're looking at and replacing the column with the values over here and calculating that, and then divide by the determinant of the sort of the augmented matrix here. So let me maybe just show you what this means by an example here. And again, Cramer's rule will basically only work if the bottom determinant is not 0, right? Because you can't divide by 0, which has to do with that invertibility criterion we were talking about earlier, but you don't have to really worry about that. So let me just show you how this works with an example. I think this will make more sense. So essentially what you want to do is, if you want to solve this system, you basically take the determinant. If you want to solve for x, you replace these coefficients with these numbers over here, calculate that determinant, and then calculate the determinant of the entire thing. And then if you want to find the y-coordinate, you replace these coefficients with these values over here, calculate that determinant, and then calculate the determinant of the left-hand side. So in both cases, when you're solving for x and y, the determinant on the bottom will be the same. It'll just be the coefficient matrix that you have over here. And this again assumes that the determinant on the bottom is not 0. So again, this matrix on the top is called dx, the one on the top here is called dy, and this is just called d. So let's look at a specific example. And again, you could use other methods to solve this, but let's say you wanted to solve this system of equations. You wanted to figure out what numbers you could stick in for x and y that will make both equations true. Well, again, we have lots of methods we could use here already, but again, we want to solve this using Cramer's rule. So essentially what you do is you calculate the determinant of the coefficient matrix here. So put down 3, 5, negative 6, 4. Calculate that determinant. So if you work that out right, you'll get 3 times 4 minus 5 times negative 6, which will give you 42. So that is basically this determinant on the bottom here, right? Or in other words, this determinant here would be 42 on both of these. And then what you do is you calculate the determinant of the top by, if you want to solve for x, replace these coefficients with these numbers. So take the same matrix you had here, but just replace the 3 and the 5 with the 24 and the 12, and then work out that determinant. So calculate that determinant. That gives you 168, right? So again, you can just take 24 times 4 minus 12 times negative 6. That gives you 168, and then that will be this determinant on the top. So basically, x should be this number divided by that number. Then doing a similar thing for y, replacing the 6 and negative 4 with 24 and 12, calculate that determinant, you'll get negative 84. So the value of y should be negative 84 over 42, which gives you 2. And that should be the solution, right? So that means that if you make x equal to 4 and y equal to negative 2, then the solution to this system, right, should be 4 and negative 2, right? If you plug those numbers in, it should make both equations equal. So that's basically how that works. And again, you can generalize this to a system of more than 2 variables. Here's another example, though. So let's say you wanted to solve this system of equations, right? You would basically just take 2 times negative 7, 5 times 3 for the determinant on the bottom. Both of those will be the same, so they'll both be... oh, sorry, there should be a 14, I guess, right? So this should be a 29 here, I guess, right? Not a 39. And then for the x, just replace the 2 and the 5 with the 1 and the 3, and then work out the determinant again, right? So it's 1 times negative 7, 3 times 3, which is 9, which gives you 16. Same thing here on the bottom. Again, you would just take that times that minus that times that, and then replace the coefficients for the y's with 1 and 3. So you'll get 2, 5, 1, 3, and then work that out, right? So 2 times 3 is 6, minus 5 gives you negative 1, and those will be your solutions, right? And again, this should be 16 over 29. And again, if you're not convinced that that's true, plug those numbers in and see what you get. So let's use Cramer's rule to solve a 3x3 system. So to use Cramer's rule to solve a 3x3 system, you basically just do what you did before. You know, the determinant on the bottom will basically be what you get when you strip out the x, y's, and z's and calculate that determinant. And then to calculate x, again, you would just replace these values with the numbers over here. To calculate dy, you would replace these numbers with these values to get that. And then for z, you would just replace this column with those numbers. So let's look at an example here. So let's say we want to calculate the solution to this system of equations again by using Cramer's rule. And I should mention, you know, if I just give you a random, system of equations on the exam and I just say solve it, you can use whatever method you want to solve it. You don't necessarily have to use Cramer's rule, but just be aware that if I ask you to use Cramer's rule on the exam, be sure that you use Cramer's rule, or you might get points taken off if you don't use the method I ask for, right? So again, you know, technically we could use several different methods to solve this system, but we're going to do this one with Cramer's rule. So I'll calculate the coefficient determinant here. So I'll just write down 1, 2, 1, 3, 5, 1, 2, 6, 7, calculate that determinant, right? And again, I'm just going to expand along the first row here because there's nothing with zeros in there. So I'll basically take 1 times that, minus 2 times that, and then 1 times that, minus that times that, right? So if I calculate that determinant, that should give me a negative 1. So that's this determinant on the bottom, that's d, right? So d, capital D in this case, is negative 1. Then I just need to do this for the dx, the dy, and the dz. So take the same determinant except replace the 1, 3, and 2 with 1, 3, and 1 if you're looking for x. So just replace that with 1, 3, and 1 and calculate the determinant. So I'll take that times that times that, minus that times that, minus that times that, that times that times that, minus that times that. If I do that, I get a 2. Right? So that means that this number is a 2, so that would mean that x then is equal to 2 divided by whatever d is, which is negative 1. So this determinant is the same for all of these, right? The ones on top will be different. So then do the same thing for y, right? Replace the 2, 5, and 6 with the 1, 3, 1, calculate that determinant. So I'd take that times that times that, minus that times that, minus that times that, minus that times that, that times that times that, minus that times that. If I work that out, I get a minus 2. So that means that d here is minus 2. And then if I calculate dz, again, I would just replace the 1, 1, 7 with 1, 3, 1. Calculate that determinant. Again, I'll take that times that minus that times that, minus that times that minus that times that, that times that minus that times that, and I'll get a 1. So that means in this case, right, the number on the bottom here, d, is always a negative 1. Dx was 2, so that would mean that x then is equal to negative 2 divided by negative 1, right? So that would be, x would be 2. Y in this case would be negative 1 divided by negative 2, which would also be a 2. I'm sorry, x was a positive 2 here, right? Yep, sorry, so that should be negative 2. And then here you'll have 1 divided by z will be equal to 1 divided by whatever d is here, right, which was negative 1, so that would just be negative 1. So your solution then is x is negative 2, y is 2, and z is negative 1. Again, if you're not sure that that's right, I mean, there's a lot of places to make mistakes here. Remember, you can always plug that back in for x, y, and z and see if it makes the equation true. So one thing I wanted to look at here is using Cramers rule with inconsistent and dependent systems. So like I said before, if the determinant is 0, then at least one of the determinants is different from 0, then the system is inconsistent, meaning that there's no solution, right? If the bottom determinant is equal to 0, right, if this thing on the bottom is equal to 0, and all the determinants are equal to 0, then the system is inconsistent and dependent, so there are infinitely many solutions. So just something to be aware of. Again, I don't think you'll really see anything like that on the exam or anything. Let's let's maybe look at some other properties of determinants here. I had some other examples I was going to do, but I think we'll skip those. And I guess this kind of goes back to what we talked about before, and that is the value of the determinant will change sign if any two rows or columns are interchanged. So here's something that will happen here, right? If I interchange the row or column, the sign of the determinant will change. If all the entries in any row or column equals 0, then the value of the determinant is 0, right? So if I have a row or column of all zeros, you don't need to calculate the determinant because it's going to be 0. And then if any two rows of a determinant have corresponding entries that are equal, the value of the determinant is equal. So in other words, if you have a row or column where these two things are equal, then the determinant will also be 0. So that might, I don't know if you're going to encounter that very often, but that might be some shortcuts you can use for calculating things. If any row or column of a determinant is multiplied by a non-zero number k, the value of the determinant is also changed by a factor of k. So let's say, for example, you multiply this top row by 3, then you basically multiply the determinant by 3. Here's another theorem. If the entries of a row or column of a determinant are multiplied by a non-zero number k, the result is added to the corresponding entries in another row or column, the value of the determinant remains unchanged. So this basically goes back to that property we were talking about before, where if you add the multiple of one row to another row, the value of the determinant will remain unchanged. Okay, so that I think pretty much wraps up that section. So the next thing we're going to look at is algebra of matrices. It turns out that matrices can be studied in and of themselves, not just for this particular purpose, and you can actually add, subtract, multiply, and divide matrices, and we'll get into that in the next section. So, okay, hope that makes sense. If you guys have questions or anything, let me know.